In this video, we're going to look at conditional probability and independence. The probability of event E, given that event F occurs, is written like this. And this vertical bar that we see in the middle here is read as given. So we read this as probability of E given F. So this type of probability where you have some given information at the back is called a conditional probability. And that's the first topic we're going to look at in this video. So here are two formulas for calculating the probability of E given F. First way to do it is to take the probability of E and F and divide by probability of F. That's our first formula. Second way to do it, you can do the exact same thing, but with numbers of elements instead of probabilities. So you could go number of elements in E intersect F divided by number of elements in F. And the second formula here is valid if all outcomes are equally likely, which is always true unless otherwise specified in a problem. So the two formulas just really come down to whether you've got information about probabilities. In that case, you would use the first formula, or if you had information about the specific sets, then you would use the second formula. In either case, you're looking at the intersection of E and F on top, and you're looking at F on the bottom. So let's try some examples of calculating these conditional probabilities. So let's say we do a survey of some students and we ask them, what degree are you doing? Is it an arts degree or a business degree? And we'll ask them, do you have a part-time job? And they'll say yes or no. So here we've got the number of students who fall into each category. So first thing we're going to do is we're going to find the conditional probability of job given business. Well, since we've got the number of students who fall into each of the categories, we're going to use the second formula where we're talking about number of elements. And we're supposed to go number in job intersect business. So that's the number of students who have a job and are in business. And what we're dividing by is the number of elements in the second set. So just the number of students who are in business. So I think I'll write the formula just beside this so that we can compare. So in general, if you're trying to find the probability of E given F, you're talking number of elements in E intersect F divided by number of elements in F. So you're dividing by number of elements in the second set. That's why we're dividing by number of business students here. So let's use the data in the table to figure this out. On top, we want the number who have a job and are in business. So let's go job, yes, and business, that's 198. So that's our top number. And what we need to divide by is the number of students in business. So we need to look at all the students who are in business and just add up those numbers. So 198 plus 2, 200. So our probability is 198 over 200. We turn that into a decimal, 0.99 or 99%. So a couple of comments to make about this because this is our first conditional probability. So first thing to notice is that business is now the new sample space. Remember, business was our given information, and we're asking, given that a student is in business now, how likely is it that they have a job? So what we've done is we've shrunk the problem down so that we're only looking at the business students now. So that's what we mean by business being the new sample space. We've now got a smaller sample space. We don't care about all students anymore. We only care about the business students. And then we say within this set of 200 students, now, what is the probability that a student has a job? So it's 198 out of the 200 business students. Second comment is I just wanted to talk about how this probability is often reported in real life. So usually when we're talking about conditional probabilities, we'll say something like, of those who majored in business, of those majoring in business, 99% have a job. So when you say it this way, this is your given information. You're just looking only at those majoring in business, or you could say that's like your new sample space. And whatever your given information is, it's always written at the back when you're writing your conditional probability in the proper notation. So probability of job given business, that's of those majoring in business, what percentage have a job? So continuing with this same data, let's do a part B. Let's find the probability that a student is in business given that they have a job. So notice that this conditional probability is now the other way around. In part A, we said probability job given business. Now we're doing probability business given job. So if we follow the formula, we're supposed to do the number of elements in business intersect job, and then you're dividing by the number of elements in the second set. So this is like saying, okay, we're shrinking the problem down now just to people who do have a job, and we're saying out of these people who are circled, now what's the probability that someone is doing a business degree? So number of elements in the intersection, we have to look at business and job. That would be our 198 students. And we're now dividing that by the number of students who have a job. So that's everyone in the blue circle. We need to add up 198 plus 87 gives us 285. You can put that into your calculator, comes out to about 0.69. So of those who have a job, 69% are doing a business degree. Right, new problem. A coin is tossed 3 times, and we're going to specify 2 events. So event E is that 3 heads appear. Event F is that at least 2 heads appear. And we want to find the probability of E given F. So let's start out by writing out our sets E and F. So the experiment is that we're tossing this coin 3 times. Event E, all the outcomes where 3 heads appear. Well, that's just one possibility there. It would have to be HHH. F is the event where at least 2 heads appear. Okay, so there are a few different ways that could happen. You could have HHT, HTH, THH. So those are all the ways to get exactly 2 heads, but we're saying at least 2 heads. So we could also allow the possibility of 3 heads. So there's F. So let's write down our formula for conditional probability. We'll figure out what we need to calculate. So probability of E given F, we need the number of elements in E intersect F divided by the number of elements in F. So what we're going to need to complete this formula is we're going to need to figure out what E intersect F looks like. So remember the intersection of 2 sets, you're just writing down any elements that are common to the 2 sets. So anything that lies in both E and F, that would be just a single outcome, HHH. So let's count the number of things in E intersect F. Well, that would be just 1 outcome divided by the number of outcomes in F. That would be 4. So 1 out of 4, or if you want to turn that into a decimal, 0.25. So let's see if we can interpret this conditional probability. Remember, the set that's described at the back is your given information. So this is like saying, given that F has occurred, F has happened, now how likely is it that E also happens? So here's F. One of these 4 things is happening, and we're saying how likely is it now that E happens? Well, it's 1 way out of the 4 outcomes in F, so 1 out of 4. So that's the interpretation of conditional probability. So new problem, let's say we're told 60% of employees are college grads, 50% of employees are permanent, and 20% of employees are permanent and college grads. We want to find the probability that an employee who is permanent is a college grad. So this is certainly a conditional probability because we're given a little bit of information about the probability that we're looking for. We just have to decide which part here is the given information. And this is where the sentence structure can be helpful. So find the probability that an employee who is permanent. This is what we know for sure about the employee. We're looking at an employee who is permanent, and what we want to know about them is what's the likelihood that they are a college grad. Now, when we write down conditional probabilities, we write the given or known information at the back. So what we know for sure about the employee is that they're permanent. What we're not sure or what we're wondering about, is the likelihood that they are a college grad. So what we want is the probability that an employee is a college grad given that they are permanent. Now over on the side, I'm going to write down the conditional probability formula just so that we've got that to look at. So we're doing probability of E given F. There's one formula that involves number of elements, and there's another one that involves probabilities. Because we're seeing probabilities in this question, we're going to use the probability version. So we go probability of E and F divided by probability of F. So let's try to apply this for this particular example. So that would be probability college grad and permanent divided by the probability of the given information. So probability that an employee is permanent. So when you're writing out this formula, you can either write probability of college grad intersect permanent, or you can just say probability college grad and permanent. Either way, you're talking about the outcomes that fall into both sets. So we should have all the correct numbers in the question. Probability that someone is a college grad and permanent is this number here, 20%. So we're going to turn that into a decimal and just call that 0.2. And we're going to divide that by the probability that an employee is permanent. So that would be 50%. So we're dividing by 0.5. And there we go, 0.2 divided by 0.5 is 0.4. In other words, 40%. So given that an employee is permanent, 40% probability that they are also a college grad. So let's look at one more fact related to this conditional probability formula before we jump into an example. You can rearrange the conditional probability formula so that it reads probability of E intersect F is equal to probability of F times probability of E given F. So if you want, I can just show you on the side how that rearranging would work. So we'd start off with the fact that probability of E given F is probability of the intersection divided by probability of F. Basically what happens here is you can multiply both sides by probability of F. So then you'd have probability of F times the conditional probability is equal to probability of the intersection. Okay, and then the fact that we've got over here just has this written the other way around. So understanding where that formula comes from, we could think of that maybe on a more intuitive level. This is saying probability that E and F both happen. If you want to calculate that, think about just calculating the likelihood of F happening. And then now that you know that F has happened, ask what is the probability that E happens given that F has already happened. And these two probabilities would need to be multiplied because you're really thinking about the sequence of events. So this is like, make sure that F happens, and then given that F has already happened, now make sure that E also happens. So I think the intuitive way of reasoning through it probably more powerful than just unraveling the formula like we did over here. So let's see if we can apply this fact. So let's say we're told 40% of employees are permanent, 30% of permanent employees have a pension. We want to find the probability that a random employee is permanent and has a pension. Well, let's see if we can just pull the information out of the question. So when we say 40% of employees are permanent, if we turn that into a probability, we're saying probability of permanent, I'm just going to write perm for permanent, probability of permanent is equal to 0.4. The second statement here, this one, is a conditional probability because we're looking now only at permanent employees. If you just look at permanent employees, 30% of those guys have a pension. So that's like saying probability of pension given permanent is 0.3. So it's important to notice when we're reading this statement here, what do we know about the employees for sure? That they're permanent. So permanent is our given information. And therefore, when you write down your conditional probability, it's probability of pension given permanent. Okay, and then let's write down the probability that we're trying to find. So we want the probability that a random employee permanent and pension. Okay, and whether you say permanent and pension or pension and permanent doesn't really matter. I think I'm going to write it the other way around, and we'll see why when we get into our calculation. So probability that someone has a pension and is permanent. So that's what we're trying to find. Okay, now I think over on the side, I will just write down the general formula that we have to work with, and we'll see how to use the information from the question. So what we said is that if you're trying to find the probability of E and F, one way to think about it is calculate the probability that F happens, and then multiply by the probability of E given that F is happening. So let's try to follow that pattern here. To get probability, pension, and permanent, we would need the probability that someone is permanent, and then we need to multiply by the probability that someone has a pension given that we know that they're permanent. So probability that an employee is permanent, 0.4, and we're going to multiply that by the conditional probability that someone has a pension given that they are permanent, so that's 0.3. If you multiply those together, you get 0.12, or in other words, 12%. So probability that an employee at this company has a pension and is permanent, 12%. So remember, our video was called Conditional Probability and Independence. So we're now going to get into the second topic of independence. So let's start with a definition. We say that events E and F are independent if the occurrence of one does not change the probability of the other. So let's look at an example from everyday life of independent events. So 2 tosses of a coin are independent. Imagine you toss a coin twice. Knowing that you got heads on the first toss tells you nothing about what's going to happen on the second toss. So the 2 tosses are independent. You've got independent events when having some information about the first event tells you nothing about the second event. Similarly, something like 2 rolls of a die would be independent. If you know that you got a 3 on the first roll, that does not change the probabilities of what will happen on the second roll. Now let's look at some examples of dependent events. So for example, the weather today and the weather tomorrow are dependent. Let's say it's raining today because there's a storm system often sitting over Vancouver Island. So let's say, it's raining today. Does that impact the weather tomorrow? Yes, probably makes it slightly more likely that it will rain tomorrow. So knowing something about the weather today does tell us some information about the weather tomorrow. May not completely determine the weather tomorrow, but it affects the probabilities. So events are dependent if knowledge about one of the events gives us some knowledge, at least some knowledge about the second event. Another example from financial markets, knowing the price of gold today would tell us something about what the price might be next week. It at least gives us a baseline for what the price has been recently. So we would say the price of gold today and the price of gold next week are dependent. So here's the key fact we're going to be thinking about when it comes to independent events. Here we have 3 equivalent statements. And when you say that you've got a list of equivalent statements, what that means is that if one statement is true, then they're all true. And if one statement is false, then they're all false. So with a list of equivalent statements, that essentially means you can look at any item on this list, decide whether it's true or false, and then you automatically know the truth value of all 3 of the statements. So that's what it means to have equivalent statements. Now let's look specifically at what the statements are. So statement 1 is that events E and F are independent, and that means exactly the same thing as item 2, which is that the probability of E given F is equal to the probability of E. So let's understand why these 2 things are really saying the same thing. See, if E and F are independent, and you're given that F has occurred, that should have no impact on E because E and F are independent. So knowing that F occurs should not change the probability of E. Therefore, the probability of E given F should be exactly the same as it was before you had the information about F. So probability of E given F should be exactly equal to probability of E. So that's only true if E and F are independent. Okay, and then a third equivalent statement that means exactly the same thing as statements 1 and 2. Probability of E and F is equal to probability of E times probability of F. So this is essentially the multiplication principle for probabilities. This will be true if E and F are independent. So let's just think about items 1 and 3 here. If we know that E and F are independent, and we ask, well, what's the likelihood of E and F occurring? We could say, well, let's just calculate the likelihood that E occurs, and then we'll multiply it by the likelihood that F occurs. If E is having no impact on F, then it should be fine to just multiply the probabilities. So we're going to do a few short examples now, just to help us understand the idea of equivalent statements and what we can and cannot conclude. So let's say we're told that probability of E is 60%. Let's find the probability of E given F if E and F are independent. Okay, well, we were told on our list of equivalent statements that E and F being independent is exactly the same thing as saying probability of E given F is equal to probability of E. And since we know probability of E, we can say probability of E given F is 0.6. Now let's do a part B and say find the probability of E given F if E and F are dependent. So think of E and F as being events that affect each other, maybe weather on different days or prices of a commodity on different days, for example. We don't know exactly how these two events, E and F, are going to affect each other. So we cannot find the probability of E given F, at least not without more information. So let's say need more info. We cannot figure out the probability of E given F because we don't know exactly how F is going to affect E. Second short example here to practice our equivalent statements, we're going to ask, are events E and F independent? And we're given some probabilities to work with here. Well, the way I would approach this is I would try to decide whether the probability of E intersect F is equal to the product of the two probabilities. So that's the question we're going to ask. If this is true, then yes, the events are independent. And if this is not true, then the events are not independent. So we're going to try to figure out whether this is the case or not. Now, notice that we weren't actually given the probability of E intersect F in the question. So another layer of complexity to this problem is that we're going to have to use the inclusion-exclusion principle first just to figure out what this probability is. So let's do inclusion-exclusion. Probability of E union F is probability of E plus probability of F minus the probability of E and F. And we'll plug in what we know. So we were told that this was 0.5, this was 0.4, that was 0.3, and we're subtracting off our unknown probability of E and F. So the 0.4 plus 0.3 gives us 0.7, and we can subtract 0.7 from both sides to get negative 0.2 is equal to negative probability of E intersect F, and we could just divide through by negative 1 here. So probability of E and F is equal to 0.2. Okay, so now we should have enough information to answer this question here. Let's decide, is probability of E and F equal to the product of the two probabilities? So I think I'm going to write down the formula that we're going to check again, just so that we can see ourselves plugging into it. And if you're checking a formula, always a good idea to put a question mark there and say, we're asking the question as to whether this is true or not. We figured out that probability of E and F is 0.2, and we were given in the question the probabilities of E and F. So let's just scroll back for a second. Probability of E was 0.4 and probability of F was 0.3. So if we plug those in, is 0.2 equal to 0.4 times 0.3? No. No, these things are not equal. So that tells us that the events E and F are not independent. So last of these short examples here, just to practice our equivalent statements. Let's say probability of E is 0.6, probability of F is 0.3, and we want to find probability of E and F if we know that E and F are independent. Well, since we're told that E and F are independent, then we can say that means exactly the same thing as saying probability of E and F is equal to just the product of the two probabilities. If you know that your events are independent, then you're allowed to use this formula. So it's just a matter of plugging in and going 0.6 times 0.3 gives us 0.18, or in other words, 18%. Now let's try part B and say, again, we want to find the probability of E and F, but this time E and F are dependent. So E and F somehow affect each other. What we need to say here is not enough info. We don't know the specifics of how E and F will affect each other, so we do not have enough information to find the probability of E and F in that situation. So another way of saying this is you can only use this formula when you know that E and F are independent. So here's a real-world problem involving independence. Let's say a plane has two independent engines. So that's a very good feature for a plane, for the engines to be independent, so that if something goes wrong with one engine, there aren't any problems expected with the second engine. Let's say engine 1 fails on 3% of flights and engine 2 fails on 2% of flights. So this sort of information would be known just from historical data, from having observed the plane over a long period of time. And so we want to find the probability that at least one engine works properly on the next flight. So when we think about at least one engine working properly, that could be broken down into three cases. So you could have engine 1 working, engine 2 fails. You could have the reverse, where engine 1 fails but engine 2 works, or you could have the situation where both engines work. And because that breaks down into three cases, we might think about using the complement rule here and say, well, maybe we can phrase this probability a little bit more nicely if we just go 1 minus the probability of the complement. So what does it mean if it's not true that at least one engine works properly? That would be both engines failing. So a much easier way to approach the problem is just to say we'll go 1 minus the probability that both fail. So if you want to see that in a Venn diagram, let's imagine the left circle represents engine 1 works, right circle represents engine 2 works. What we're looking for is this probability here, but we could say, oh, well, let's just go 1 minus the outside region being this situation where both engines fail. And that's a more direct way of solving the problem. So now it comes down to figuring out this probability that both engines fail. Because the engines are independent, we can say, well, that's just the probability that engine 1 fails times the probability that engine 2 fails. And it's very important here, I think, to point out that we're able to draw this conclusion because we're told that the two events are independent. So if we were not told that in the question, we wouldn't be able to do this step of reasoning. So that's just coming from the fact that when two events, E and F, are independent, that tells you that you can use the formula probability of E and F is just equal to the product of the two probabilities. So now we can plug in and solve. So we're going to go 1 minus probability that engine 1 fails. That's 3%. So let's write that as a decimal, 0.03. Probability that engine 2 fails, 2%. So 0.02. Can grab your calculator, and that comes out to 0.9994. So this is the probability that at least one engine works properly on the next flight, 99.94% probability of that happening. Now, occasionally we may see situations where we've got 3 or more events. So let's do a quick definition for what an independence means in that context. We'll say a set of 3 events is independent if the probability of, let's call our events E1, E2, E3, probability of E1 and E2 and E3 is just equal to the product of the 3 probabilities. So that's a definition of what independence means in that context. And there are similar formulas for more than 3 events. So if you had, say, 7 events, it would be the probability that all 7 events happen is equal to the product of the 7 probabilities, for example. Okay, let's say a product has 3 independent parts. So this could be like a laptop. You could say the 3 independent parts are like the keyboard, the screen, and the processor, something like that. So if something goes wrong with one, we're not expecting anything to go wrong with any of the other parts. In a year of use, let's say part A fails 1% of the time, and we've got similar information for part B and part C for how often they fail. And what we want is the probability that no part fails in a year of use. Okay, so let's define some events just so that we can write down our probability a bit more clearly. So let's say event A is the situation where part A fails, and therefore the complement of A would be part A does not fail, or part A is still good after a year of use. And let's write down the probabilities that we know from the question. So if A is the event where part A fails, we're told the probability of that happening is 1%. Therefore, the probability of A complement, we're just going to go 1 minus that probability. It would be 99%. So 1% probability that part A fails after a year, 99% probability that part A does not fail after that 1 year. And we could do similar things for part B and part C. Now, what we're ultimately looking for is the probability that no part fails. So let's see if we can write down the probability that we're going to be looking for. We want A to not fail, and we want B to not fail, and we want C to not fail. We want no part to fail. So that would be A complement intersect B complement intersect C complement. We want part A to be good, and we want part B to be good, and we want part C to be good. So the probabilities we actually need are the probability of B complement and probability of C complement. Okay, so let's reason through those in a similar way. Probability of B is 2%. So probability of B complement, 98%, or 0.98 if we write it as a decimal. Probability of C is 4%. So probability of C complement, 96%, or 0.96 if we write that as a decimal. So the probabilities that we actually care about here are the probabilities of the part being good, 99%, 98%, and 96%. Okay. So the probability that we're trying to calculate, probability that all 3 parts still stay good, it would be tempting to just say, well, this is going to be the product of the probabilities. So probability of A complement times probability of B complement times probability of C complement. And we are allowed to do that as long as we know that these events are independent. Remember, we were told in the question that the 3 parts were independent. So that's why that line of reasoning is valid. So it's just going to come down to then multiplying our probabilities together. So 99 or 0.99 is our probability that A is good. 0.98 is our probability that B is good. 0.96 is our probability that C is good. If we multiply those together, it comes out to about 0.93. So you've got about 93% chance that your laptop or whatever this is will still be good after a year. So it was really critical here that the 3 parts were independent. If you had dependent parts where one is more likely to fail if another one fails, then it wouldn't be valid to just multiply all your probabilities together, and you would need more specific information about how the events are related in order to solve the problem. So you may remember back in our video on section 4.1, we talked about what it meant for two events to be mutually exclusive. And we've just now in this video talked about what it means for two events to be independent. And it's pretty common that people have some confusion or some questions about really how these two concepts are different. So I want to just draw you two pictures to show you the difference between these two concepts. So let's start with mutually exclusive. If we say two events, E and F, are mutually exclusive, that means they cannot occur at the same time. So if you look at the number of elements that are in the intersection, it's 0. So I'm actually going to label this outside the diagram. I'm going to say number of elements in E intersect F is 0. Or if you were talking about probabilities, you could equally well say the probability of E intersect F is 0. So mutually exclusive just means can't happen at the same time. That'd be something like, I'm wearing slippers and I'm wearing sandals. I can't do both at the same time. So wearing slippers, wearing sandals are mutually exclusive, just to sort of give you a silly example. Saying that two events E and F are independent is a more conceptually complicated idea. What we're saying is that if two events are independent, then knowing that one occurs does not affect the likelihood. It doesn't change the likelihood of the other one occurring. So a good way to visualize that is to say the probability of E intersect F is the probability of E times the probability of F. So this is something like rolling a die 2 times, or flipping a coin 2 times, or 2 independent engines on a plane having a successful flight. So that's our video on conditional probability and independence. Thanks for watching.